what I'm trying to explain right now, you need to understand what we mean by parameter and statistic. Okay. Now, you know, we find ourselves in a world where we actually want to understand what is around us. We want to understand our political environment. We want to understand economic environment. We want to understand medical environment. Just like right now, there's a pandemic in the world, and we're trying to look for a way. There's a kind. Every country is trying to look for a way to be able to control the COVID, and how they can totally put that under control. That's what we're trying to do. So, which means for them to be able to have a way out, of course, they need information. Okay. And you know what? When we say parameter, okay, parameter is just a numerical it's a numerical descriptive measures of a population. So let me just tell you in an ordinary language, I'm actually going to say parameter is whatever we want to know. Okay, what we seek to determine. We may actually want to know, okay, what is the number of people with the COVID. We want to know probably what is the proportion in an election, what is the proportion of those that will actually vote for a particular candidate, or maybe we actually want to figure out what is the average annual income in a particular country. That is what we call parameter. Anything that we want to know, anything that we're seeking to know, okay, that's what we mean by parameter. So which means parameter could be mean, it could be proportion, it could be variance, it could be standard deviation. Therefore, their parameter is an attribute of a population. Okay, so which means whatever we want to know, okay, then if we really want to get information about what we want to know, then we need to go back to the population. That's exactly what parameter is talking about. But you know what? We don't have resources to study entire elements in the population. Okay, because of that, we are not likely to get parameter. Because, for instance, uh, if we want to know, if we want to get the parameter exactly, it means every item in the population of interest has to be investigated. Okay, and you know what? What we normally do in research, you don't study every item in the population. What we always want to do is to take a sample from the population. Okay, so when we take a sample from the population, whatever we compute from the sample is what we call sample statistic. Take a look at that. Whatever we compute from the sample is what we call sample statistic. Okay, so if we want to find the mean, just like before this election, there have been opinion poll about the likely winner. Okay, so in the opinion poll before election was decided, of course, they did not interview all the eligible voters in the country. Okay, so whether the Fox News, the CNN, and so on like that, if they are carried out their investigation, they're actually going to collect sample, okay, of voters, and they're going to ask them question, or who are they going to vote for? Okay, so which means in every study, well, we normally, if we actually want to provide information, if we really want to understand what the parameter, so what we're going to do, we don't study the entire elements in the population. So what we do, we take a sample, and when we take a sample, whatever we want to find will actually be obtained from the sample. So whatever that we compute from sample is what we call sample statistic. Okay, that is and that is why I said it's a numerical, descriptive measure of a sample. It is calculated from the observation in the sample. If I want to find my mean, I'm actually going to do that from the sample. If whatever I want to find, whatever that is characteristics of interest. Okay, so the next thing that I'm going to show you right now, because I actually wanted to see the difference between the sample statistic and the population parameter. Of course, like I said, you know, the parameter, these are the symbolic representation of parameters. Okay, mean, we got it. The symbolic representation of mean is this guy here. The standard deviation is this guy here. The variance is this guy here. Proportion is this guy here. So these are the symbolic representation of the population parameter. So what I'm trying to tell you right now is that the population parameter could be mean, could be standard deviation, could be variance, could be proportion. Okay. So if you take a look at, because we are not going to investigate, we are not going to uh, actually consider all items in the target population, then what we're actually going to do is we're going to take a sample. Then it means when we take a sample, when we're looking for the population mean, at the end of the day, what we're going to end up getting is going to be sample mean. Okay, when we're looking for the population standard deviation, what we're going to end up getting is going to be sample standard deviation. When we're looking for this population variance, we're actually going to compute sample variance. When we're looking at the population proportion, what we're going to end up getting is going to be sample proportion. And at the end of the day, you know, what we're going to do, we're going to refer to all these guys as the estimate of the population parameter that we're looking for. Okay, that they're going to be estimates. Can you get it now? Okay, so I'm just trying to show you, the possible population parameter we'll be looking for, and as well as their corresponding sample statistic. Like I said, we live in a world where we need information to be able to understand the world around us. Okay, we may be interested in obtaining the average. We may want to find the standard deviation of a process. We may want to find the variance of a process. We may actually want to figure out the proportion. Okay, for instance, the proportion, maybe I actually want to estimate the proportion of those who have a particular disease, or the proportion of female in the United States Congress. Okay, so I may decide I want to look at that. Okay, so, and of course, I don't really need to investigate everyone in the target population before I can actually do that. Okay, so well, I'm actually going to take a sample size, and whatever I want to compute, whatever I want to get, then I'm actually going to compute that from the sample. That's exactly what I'm going to do. Okay, so now now what is it mean? What is sampling distribution? Today's course is sampling topic is sampling distribution. So how does sampling distribution actually connect with what I just explained right now? Now let me give you an example. Okay, now before the election, you know, uh, Fox News, CNN, MSBC, ABC, those are the media organization in the United States of America. You know, they conducted an opinion poll. Okay, and you know what? Uh, the value that the CNN got is different from what the Fox News got. Why do they have to get a different value? They actually get different value because they selected people at random, and they are not likely to use the same set of respondents. Okay. Now, how do we now know the one that is telling the truth? Okay. So if we want to know the one, so which means if different investigators, okay, should conduct a study, okay, maybe they want to conduct a study on the mean. Maybe they probably want to get the average household income in the United States, or they want to get the average income in a particular country. Okay, so if they work on that, of course, they're going to select different sample. Okay, so when they select different sample, of course, they're going to have this different results. And how do we now tell? How do we know the particular researcher that have the good result, or how can we really tell, okay, about the true value of the parameter that we're looking for? And that is the reason why the idea of sampling distribution will be used. So the sampling distribution of a sample statistic, when I say sample statistic, I mean the sample mean, the sample variance, the sample standard deviation, or the sample proportion. Okay, so of it is the probability of distribution of the sample statistic is what we call sampling distribution. So why do we need probability distribution of sampling sample statistic? Because uh, across researchers or from sample to sample, even the same researcher, if I'm conducting a research right now and I choose a sample size, I compute my mean. If I go into that population again and I choose a sample size as random and I compute my mean, I'm actually going to get a different result. Okay, therefore, to harmonize the situation, then I need to use the knowledge of sampling distribution will be used. Okay, now what sampling distribution is going to talk about is that with a sampling distribution, we're actually going to know the you know the possible value the statistic can be. Okay, the possible value the statistic can be, and at the same time we'll be able to find the probability distribution. We're also going to have the probability distribution associated with each statistic. Okay, and what is probability distribution now is the probability distribution is just going to tell us what is the frequency, what is the number of time this particular statistic occur. Because the number of time a particular statistic occur, that could be an agreement among the researchers. I work on something, maybe the result I got maybe is not totally different from what another researcher got. Okay, if we got the same result, of course, the frequency, associated with that is three people get the same result, the frequency is going to be three. Okay, so which means every statistic have different probability. Okay, so which means the classical approach in probability does not operate right here, because the classical approach in probability, we're actually going to tell you that for every element in the sample space, every outcome has equal probability of occurring. But here they don't have equal probability of occurring, because some outcome we have a greater probability of occurring than others. So that is what the sampling distribution is talking about. So the sampling distribution is a probability distribution of sample statistic. Okay, the probability distribution of sample statistic, which will enable us to know the possible number of the value of statistic that we can have with the corresponding probability. Oh, can you guys confirm if you guys are still hearing me? Uh, okay. Oh, okay. Thanks for confirming that. Now, I'm actually going to go to I want to demonstrate something to you right now. Take a look at what I'm projecting right now. Okay. Suppose we have a population of 4 people. Okay. Take a look at this. I got 4 people right here. Okay. And that is why the population size equal to 4. So we have 4 people. Okay. Now, uh, of course, the random variable X is actually going to be from 1 to 4. Okay, that's going to be random variable X. And you know what? If I want to choose any of these people, maybe these are my students and I'm trying to investigate something, and I don't want to use all of them, and I actually want to probably call on, choose anyone at random. Okay, you know what? If I want to choose anyone at random, I need to assign a number to them, and that is what I'm assigning right here. Number 1, number 2, number 3, number 4. And of course, the probability of choosing any one of them is going to be uniform. Okay, it's going to be uniform because all of them we have equal probability of being chosen. Okay, that's going to be uniform. Okay, now if that is the case, let us assume that if I want to find a population mean, I told you what we're looking for. We're looking for population mean, but uh, the population mean, to get population mean, it means I need to add all the observation together and divide by the number. But you know what? I want to use this to demonstrate to you right now that instead of you to compute population mean, if you do the sampling distribution, you're actually going to get the same result with the population mean. Okay, you know what? We have just 4 students, right? 4 people right here. In a situation where we have thousands of people, you don't need to study all of them. That is what I want to demonstrate to you right now by making use of a sampling distribution. Okay, I want to tell you what you're going to get using everybody is what you are going to get when you take sample. Okay, and that's exactly what I want to demonstrate to you right now. But you know what? In my demonstration, I will first start with this. I will first trying to look at the distribution of the population. You know, I told you the other time, if I have 4 people in this population, okay, of course, they're going to be uniformly distributed. And of course, the probability of choosing any one of them is actually going to be 1/4. Okay, 1/4 is going to be probability, which is actually going to be 0.25. And take a look at the bar right here. And that is why you have all the bars, you know, the probability of choosing that, number 1% or number 2%, number 3%, number 4%. You can see the bars are equal. That is at 0.25. So which means the probability distribution of this population right now is uniform. Okay, the probability distribution right now is uniform, and this is what is indicating that. Okay, so um, another thing, another thing that I want to talk about is I want to talk about the mean. I want to talk about the mean. Okay, I want to talk about the mean. Now, if I want to get the population mean, okay, now what I'm going to do, I'm actually going to sum, the observation together, and I'm going to divide by the number. Now, what are the observations right here? Okay, I want to find that summation n divided by that. I have 1 plus 2 plus 3 plus 4 divided by 4, right? Okay, so this is actually going to be 10, right? So what is 10 divided by 4? 10 divided by 4 is going to be 2.5. That's what you have here. Now, this is for population mean, okay? But you know what? I said we are not going to make use of all the data set in the population because we don't carry out what we call complete enumeration. What we do is a partial enumeration where we don't need to study everybody in the population before we can have a result. Okay, we don't need to study everybody in the population before. But what I want to demonstrate to you right now, sorry, give me 1 second. Can you guys confirm if you guys are hearing me? Because I get a lot of children at home today, so I'm so sorry about that. Okay, so this what I presented to you right now, you have the population mean, and we can say the distribution of the population is uniform. Okay, and I want to demonstrate to you right now, uh, despite the fact that we have the population mean to be 2.5, but the distribution here is uniform. Okay, what we're actually going to do is to first see, we actually want to use the idea of sampling distribution uh, right here, and you're actually going to see whether we're going to get the same results. Okay, now this is what I'm going to do right now. Give me 1 second. This is what I'm going to do. Now, do you know that if I have 4 people, like I said, I got 4 people, okay? And if I want to choose, and I need to disclose if I want to take sample, but probably I want to take a sample of 2, right? Okay, so let's assume that I want to take a sample size of 2. I'm not interested in all the 4, okay? All the 4 people. I'm only interested in 2, okay? Now, I need to first, if I'm sampling with replacements, okay, what is going to happen if I'm sampling without replacements? What is going to happen? So what I'm going to do right now, I'm going to show you if I'm sampling with replacement, what is going to happen. Okay, so you need to first write 1 2 3 4, then you write 1 2 3 4, and these are the possible pairs. Take a look at that. These are the possible pairs. Okay, if I'm sampling with replacement, okay, if I'm sampling with replacement, of course, if I choose number 1 person and I replace that, And since I'm actually going to be sampling at random, there's possibility that I'm actually going to choose the person that I choose in the first place. I'm actually going to choose that at a second occasion. You know that, and that is the reason why we have. That's why we have 1 1, 2 2, 3 3, 4 4. So what I'm trying to talk about now, these are the possibility. Okay, and you know what? Um, another, if we want to know what is a possible number of pairs you're actually going to have, the possible numbers of pairs where you are sampling with replacement is actually going to be population size raised to power sample size. Okay, you know this population size was 4, right? And the sample size is 2. Okay, what is 4 raised to power 2? That is actually going to be 16. Okay, and that is the reason why I have this combination. Can you see that now? So that is why I actually have that. Now the next thing I'm actually going to do, I need to find the pairs of mean. 1 plus 1 divided by 2 is going to give me this guy here. I'm actually going to find the mean of each of these, okay? I'm going to find the mean of each of that. I'm going to find the mean of each of that, okay? And to find the mean of each of that, take a look at that. When I find the mean of each of that, the means of each of the pair, I'm actually going to divide by 2. When I do that, I'm actually going to have this. Take a look at that. 1 plus 1 divided by 2 is actually going to be 1. And 1 plus 2 divided by 2 is actually going to be 1.5. Okay, so what I have here right now is actually the sample means. Okay, how many sample means do we have? We got 16 sample means. Okay, we got 16 sample means. Now what am I trying to showcase right here? I'm trying to showcase situation whereby different investigators actually work on something and they are getting different results. Take a look at this. This is more or less like the result they have. And then if you take a look at what I have here, we got a situation whereby some have the same result. Look at 2, 2, 2. Can you see that now? And that is, situation where you have some numbers are being repeated. Of course, you're going to be talking about probability distribution. Of course, if you take a look at what I have right now, you're actually going to say some particular numbers actually occur more frequently than others. Okay, so therefore this is my statistic right now. The statistic actually here is the mean. Okay, the statistics here is the mean. You can see that now. Okay, so if the statistics is the mean, okay, I got 16 means right now. Okay, take a look at that table. Okay, now the next thing I'm actually going to do right now is to be able to, give me 1 second, take a look at this is this means that I talk about. Can you see that now? Then I can actually do this. I'm going to write x bar. Okay, I'm going to write the probability of x bar. Okay, based on that table right now. And what is the smallest value? The smallest value is actually 1. Okay, so you're going to have 1.5. You're going to have 2. You're going to have 2.5. You're going to have 3. You're going to have 3.5. And you're actually going to have 4. Now, when you take a look at what I have here, the smallest value is 1. The largest value is actually going to be 4. Take a look at that. Now, what I'm constructing right now is this is a probability distribution. We're no longer talking about the probability distribution of random variable x, but we're talking about the probability distribution of the mean of the means. We got different kind of means. Okay, so the probability distribution of different kind of means is what we call sampling distribution. Okay, now how many 1 do we have? We got 1 over 16. Okay, we're looking at the table. How many 1.5? That would be 2 over 16. How many 2? We got 3 over 16. Take a look at that. How many 2.5? We got 1, 2, 3, 4. We got 4 over 16. Okay. How many 3 do we have? We got 3 over 16. Can you see that now? And how many 3.5 do we have? We got 2 over 16. Then how many 4 do we have? We have 1 over 16 in such a way that when you add all this probability together, it's actually going to be 1. Okay. Now, the table that I generated from this data right now is what we call sampling distribution. We are not going to call it probability distribution. This is sampling distribution because this is a probability distribution of a sample statistic. Okay. And the statistic right here is the mean. Now, if I plot this guy here against x bar, look at what I'm going to have. the distribution has changed from uniform to normal distribution. And you know what? Um, the reason why some researchers argue that out, that working with sample is even better than working with a population is because take a look at the way we started. We started, the population of the distribution was not normal; it was uniform. You understand what I mean? And the best distribution in statistics is normal distribution, because with normal distribution, we're going to have a very small degree of variability. Okay. Now take a look at what we have now. When we look at the probability distribution of the sample statistic, take a look at what we're having now. The distribution is now normal. Take a look at that. Look at the distribution now. This is the histogram. You actually saw what we plotted. This is normal now. Take a look at that. Okay, the next thing that we now want to do, we want to find, take a look at this guy. This guy is what we call sampling distribution. Sampling distribution, okay? That's what we call mean, the mean of sampling distribution of sample mean, okay? The mean of sampling distribution of sample mean. If I want to get the mean, do you know what I'm going to do right now? What I'm actually going to do, I'm actually going to go back to the pairs of mean. I'm going to add all this together. Okay. When I add all that together from 1 plus 1.5 plus 2, or if you don't want to do that, you can actually, the other time I actually created a table where I have X bar and the probability of X bar. You remember, if you want to find the mean, you can just multiply that by that. You remember the formula that we normally use, summation P X bar, P of X bar. That's another way you're going to get your mean. Okay. Only that the random variable here is not X, but the random variable is the mean, is a sample mean. Take a look at that. Okay. Or basically, you can add everything here together and divide by 16. When you do that, what are you getting now? You're going to get the same value that we got the other time when we're, under the population mean. Do you remember? Look at the value now. This also gives 2.5. Take a look at that. That also gives 2.5. Okay. I'm going to show you what we got when we're dealing with the mean the other time. Take a look at that. We got 2.5. Can you see now? And what do we get at the end of the day? We also get 2.5. Pay attention to the symbol here. This particular symbol means the mean of the sampling distribution of sample mean. Is different from this. This is just population mean. Okay, the population mean is summation x divided by n. You remember that? But this guy here is the mean of the sampling distribution of the sample mean. And of course, we're getting the same result. Okay, so a chart came in right now. I'm going to read my chart. Somebody says, so the sampling distribution is a graph showing all possible samples. You are right. You are very, very correct. It is not only showing the possible sample, it's also showing the probability associated with that. Number one is going to show the possible values of statistics that we can have. And at the same time, it's also going to show probability associated with that. Does that make sense to you now? And that's exactly what we mean by by sampling distribution. Okay, so you are right. Okay, so the next thing that I'm actually going to talk about now is this. Now, take a look at this. We started with this population that was uniform. We computed the mean. The mean was 2.5. And when we introduced the idea of sampling distribution, what happened? I got a normal distribution, and I still have the same value for mean. Take a look at that. But you know that the one that we're actually going to prefer is this guy here, okay, because of the shape. The normal distribution is highly preferred in statistics because though they have the same mean, but let me tell you this, the variance associated with the sampling distribution will be smaller than that of the other one. Okay, and that is the reason what we care about. We care about the variation. We care about the variance. Okay, we care about the degree of variability. That matters a lot. Okay, so take a look at that. Okay, so the next is before I go to the next, you know, the next subtopic. Is there anyone who need clarification? Can you guys confirm if you guys are hearing me clearly? Okay, thanks for confirming that. Now, the next thing that I want to talk about now is the sampling distribution of a sample mean and the central limit theorem. Okay, and let me tell you this. Um, if we actually want to investigate, we're actually going to go to population, and the population from which our data set is actually going to be drawn from could be normal or not. Okay, and you know what? Uh, if a population is not normal, of course we know what to do to make it normal because, like I said, because of the simplicity and tractability of normal distribution, and because of the fact that the variance associated with a random variable that is distributed normally, of course, because the variance is going to be small, and that is the reason why we care about the nature of our population, and we know what to do. Okay, and that is what the central limit theorem is actually going to tell us now. Now, by central limit, okay, you want to ask question? Okay, now by central limit theorem, now um, the central limit theorem is just trying to tell us that for us, for the population to be normal, we actually, uh, I mean, we know that the population may not be normal. What are we going to do? Something needs to be done. And what we can do is to actually use the idea of sampling distribution, then it's going to return us back to normality. But you know what? That depends on the sample size. Okay? Now the sample size has to be sufficiently large. So how large is a large? And therefore they recommended that it has to be at least 30. Now we're actually going to have proposition right now, number one. The mean of the sampling distribution is equal to the mean of sample population. Take a look at this. Expected value of the mean. We got different kind of sample mean. The average of that will automatically give us the population mean. That is a belief in statistics. When you work with a sampling distribution, we have different kind of means, then you put into consideration the sampling distribution of that, where you actually consider possibility. Okay, we believe that the mean of the means will give us the population mean that we're looking for. The standard deviation of the sampling distribution is a ratio of the standard deviation of the sample population to the square root of the sample size. Okay, now let me tell you this. If you take a look at this guy here, that's a sigma, which actually represents the standard deviation. And that is the standard deviation of the sample population that may not even be normal. Okay, and you know what? If you take a look at this guy here, is actually the standard deviation of the sampling distribution, which we also call the standard error. We believe this guy is actually going to be smaller than the standard deviation of the parent population. Okay, so that is a belief. Like I said in research, uh, what we want to do is actually to model reality. But you know what? In modeling reality, our model cannot give the exact picture of reality because there's no perfect model anywhere in the world. Okay, there's always going to be an error, no matter how perfect a model is. I remember what George Box said some years ago. George Box said, and I quote, "All models are wrong, but some are useful." Okay, the reason why he said all models are wrong and why some are useful is because it is not all models that will actually deliver, that will do the job. So, but I want to tell you that if you put every necessary machinery in place, of course, you're actually going to have models, that will actually do the job. But you know what? No matter how perfect a model is, there's actually going to be what we call error. That's what we call an unexplained variation. it is not everything about the about life situation that the model that we're trying to use can actually explain. There's always going to be what we call an unexplained variation. I think you get it now. There's going to be unexplained variation, and only that what we're trying to do is to see how we can minimize this unexplained variation. But no matter how we try, it can never be zero. And that is the reason why at times, it's going to look as if our models are failing us. Our models are not failing us, only that we're not paying more attention. We need to pay more attention because the models we're using, they actually have assumptions, and assumptions are the limitation, okay? And you know what? These assumptions need to be investigated because it is not all the time that this assumption could hold. So that is the reason why we need to revisit this assumption, because models are good. Model is as good as assumption putting into a model. Can you guys confirm if you guys are hearing me clearly? Okay, thanks for confirming that. Okay, so because of that, we're going to be talking about the standard error of the mean. Initially we were talking about the standard deviation, and the standard deviation has to do with the standard deviation of the random variable x that may not necessarily follow normal distribution. But you know what? If I want to talk about the standard error of mean, we believe that the standard error of mean is the standard deviation that has been adjusted because we have incorporated the idea of sampling distribution. And of course, the error that we're going to have now will actually be minimized. Okay, that is exactly what we're going to do. I think I'm actually going to stop here today. I'm going to continue from here next time. Is there anyone who want to ask question before I go today? Is there anyone? Can you guys confirm if you guys are here hearing me clearly? Can you hear me clearly? Okay. I need you to comment right now if everything that I've explained, if you really understand everything that I've explained. Okay. Somebody said, would there be a midtime two review? Yeah, there's going to be a midtime two review, and that will be done on Monday. Okay. So the lecture on Monday is actually going to center on midtime two preview. Okay. And where I'm actually going to tell you some necessary material areas the midterm tool is actually going to cover. But before Monday, what I actually wanted to have in mind is that uh, everything that we did up to Wednesday, okay, everything that we did up to Wednesday, what we're doing right now will not feature in midterm two. Okay, like I said, the focus on Monday of the lecture of Monday is actually going to be on midtime two preview, where I'm actually going to extensively review some possible areas and questions. Okay, is there anyone who have another question? Is there anyone? Is there anyone that want to ask another question? Is there anyone? Everything that I've presented today, really understand it. I need you to comment yes. You understand everything that I've explained. If everything okay, good job, good job. Thank you so much. Okay, so which means you understand that. Okay. So if there is any one of you, let me just tell you this because of the fact that you're going to have an exam next week. I'm actually going to extend the deadline for submission of the homework aids. I'm going to say that again because of the fact that you have a midterm two next week. Uh, and I know the submission of the midterm 8 is due on Sunday, but you know what? I'm actually going to extend that because I want you to have more time to prepare for your midterm too. Okay. And you know what? Uh, I'm actually going to, uh, let me see. Like I said, I'm going to have review on Monday about, on the possible areas. Okay. So until Monday that I'm actually, let me just for say, I want to appreciate everyone who have attended my lecture today. I hope you guys enjoying it. Please make sure you stay safe, okay? Somebody said, is there going to be a practice mid-time? Yeah, that was what I said. There's going to be a practice mid-time on Monday. The focus on Monday is actually going to be on the practice mid-time. That's what I call mid-time to prevail. Does that make sense to you now? The person that asked that question, okay, you get that. Okay. So I want to appreciate everyone for attending my lecture today. I hope you enjoyed the lecture. Until Monday that we're going to come your way again with another exciting topic. With a review, the midtime to review. Make sure you stay safe and have a good weekend. Bye for now, guys.